In the last lessons, we discussed what is a linear programming problem and how to formulate linear programming problems. Now we will see how to solve linear programming problems, and there are 3 methods to do it. One is graphical method, where we draw a graph and find the solution. Then an analytical method called simplex method. Then there are many optimization software that can be used to solve linear programming problems. Even we can use Microsoft Excel to solve problems. In this lesson, we will see how to solve linear programming problems graphically. Graphical method can be used to solve linear programming problems with 2 decision variables. Let's take one example. This is a maximization problem with 3 constraints with 2 decision variables. In graphical methods, all the constraints have to be graphically represented in the same coordinate plane. Now, look at our constraints. All constraints are inequalities. So, we will have to graphically represent all these inequalities. Before drawing a linear inequality, we have to first draw the corresponding straight line. Our first constraint is x plus 3y is less than or equal to 12. So, we should first draw the line of x plus 3y is equal to 12. In order to draw a straight line, we should know at least 2 coordinates. Using the equation of the line, we can find 2 coordinates. What we can do is we can substitute a value for one variable, then we can get a value for the other variable. So, one coordinate is completed. In similar way, we can find another constraint. The easiest way to do this, we can substitute 0 for one variable, and then we can find the value of the other variable. Then next time we can substitute 0 for the other variable. Now considering our problem, take x plus 3y is equal to 12. First substitute 0 for x. Then we will get y equals 4. So 0, 4 is one coordinate. Now substitute 0 for y, and then we will get x equals 12. So 12, 0 is another coordinate. Now we have 2 coordinates, 0, 4 and 12, 0. We can plot them in the coordinate plane and join them by a straight line so that it is the line for the equation x plus 3y is equal to 12. Similarly, we can find 2 coordinates for each of the other 2 equations as well. Once we draw the straight lines, we can then mark the inequalities. Look at this coordinate plane with x and y axes. We know we have non-negativity constraints. That means both x and y are positive. So we only need to use this part of the coordinate plane. Now let us draw the inequalities. We will start with 5x plus 9y less than or equal to 45. First, we will draw 5x plus 9y is equal to 15. 0, 5 is the first coordinate and 9, 0 is the other, and this is the line. Then we will mark the inequality of less than. To mark it, we have to shade the less than side like this. Similarly, we can mark the other inequalities as well. Now, where is the solution? The solution should satisfy all the constraints. That means we have to find x and y that satisfy all the constraints and also give the maximum value for objective function. This is the common area for all the constraints, and this is called the feasible region or solution space. Feasible region means that the solution is possible in this region. Now, theoretically, what we have to do is we have to substitute coordinates of all the points in the feasible region in the objective function and select the point that gives the maximum objective function value. But the problem is that we have infinite number of points in this feasible region, and we cannot practically do it. But there is a theorem that if the feasible region is a convex figure, the solution exists at one of the corner points of the feasible region. Now, this is a convex polygon and the solution exists at one of the corner points. This is the procedure. There are 5 corner points. We have to find the coordinates of those points and substitute in the objective function. Then select the coordinates corresponding to maximum objective function value. For minimization problems, we have to select the coordinates corresponding to minimum objective function value. So, we need to find the coordinates of O, A, B, C, and D. But we already know the coordinates of O, A, and D, and therefore we need to only find the coordinates of B and C. If this is drawn on a graph sheet according to the correct scale, then we can measure the distance and determine the coordinates, and that is the correct way. Or what we can do is we can solve the equation and find the coordinates of B and C. Accordingly, the coordinates of B are 7.620.77 and the coordinates of C are 4.52.5. Now find the objective function values corresponding to each point by substituting the coordinates in the objective function, that is 2x plus 4y. This table shows the objective function values for each point. We can see that the maximum value is 19 and the coordinates corresponding to that value gives the optimal solution. That means the optimal solution is x equals 4.5 and y equals 2.5. Maximum z is 19. So that concludes the solution. Now I will show that this optimal solution satisfies all the constraints. This is an additional part illustrated for your knowledge and not a part of the solution. See, we have 3 constraints. We will take the left-hand side of all constraints and substitute the optimal solution. The left-hand side of the first constraint is x plus 3y. If we substitute x equals 4.5 and y equals 2.5, we will get 12. The constraint says it should be less than or equal to 12. That means the constraint is satisfied. Similarly, we can see that the other 2 constraints are also satisfied. That means the optimal solution gives the best solution within the limitations. Let us take another example. Before using the graphical method, we have to formulate this problem mathematically and write a linear programming problem. We did this example in the last lesson, and therefore I am giving the formulation now. If we take x1 and x2 are the numbers of tables and chairs to be manufactured respectively, the linear programming problem related to this question will be as shown here. Now the steps of graphical method can be applied as you learned. Then this is the graphical representation of the constraints and feasible region. There are 3 corner points and we can use the coordinates to find the objective function values as shown in this table. Accordingly, 10, 20 is the maximum value and the optimal solution is x1 equals 35 and x2 equals 20. The maximum profit is $1,020. There are some special situations that you will identify from the graph. Look at this graph. We can see that the feasible region is not a closed figure, and that means the solution is unbounded and we cannot find the optimal solution. In some cases you'll get graphs like this. Here there is no common area to all the constraints. That means there is no feasible region, and therefore we say that the solution is infeasible and therefore we cannot find the optimal solution. Finally, there are both advantages and disadvantages of this graphical method. I want you to think about those advantages and disadvantages by yourselves.